This is 2012 Scholarship Physics paper question 3 on the Doppler effect. We've got the speed of sound in the air and acceleration due to gravity given. Both do, well actually speed of sound is 2 significant figures, acceleration due to gravity is 3. When the Doppler effect occurs, it's known that the apparent frequency of a sound is increased as the source of the sound moves towards a stationary observer. Explain why the frequency increase occurs. So this is your standard Doppler effect explanation. I won't go into a lot of detail, but you should hang it on F equals V over lambda. The speed of sound does not change, so V is no change at all, but the wavelength is decreasing as something moves towards a stationary observer. So the relative velocity of the source compared to the observer is well, there is a relative velocity between the source and the observer, and that has the effect of bunching up the wavefronts. So what we might say is the wavelength is shorter, if we're being really precise. Shorter due to the following wavefronts, or wave crests is probably a bit better. You could explain what a wavefront is, but sometimes people don't use it consistently. So if you talk about wave crests, that's got a clear location. So it's shorter due to the wave crests being produced closer to the previous wavefront crest, or that it was produced, than it would be if it was stationary. So the observer hears the sound, the wave crests, each of those amplitude peaks arriving closer than if it was not moving towards them. Anyway, and that has a result. If you decrease the wavelength, you have to increase the frequency according to F equals V over lambda, which is V equals F lambda rearranged. Part B, explained qualitatively. So we don't have to do calculations because that would be quantitatively, quantity being a number or a fixed amount. Anyway, qualitatively, what would happen to the apparent frequency if the observer moved at a constant velocity towards the moving sound? So this time it's the observer who is moving, so the observer is moving, and you've still got the same moving source, so exactly the same as A, but this time observer's moving closer. So what would happen if we're talking in terms of relative velocity? Okay, so the relative velocity is higher, and you could say that the apparent wavelength is going to be therefore shorter again, but that's not actually as good because it's not as grounded and something easy to talk about. If you look at your relationship between the time period and the frequency, it's 1 over f, or the frequency is 1 over the period, and what's actually happening, because your wavelengths aren't being shorter this time, but your observer is hearing them with less time period between successive crests, which has the effect of decreasing the period. So the period is decreasing, therefore the frequency must increase further. So you'll have an even higher apparent frequency than an A. Okay, so those are just your qualitative ones. Now we get on to some actual quantitative, some calculating type things. Ben is on the top floor of an apartment building. Let's just draw this really briefly. Helps our visualization. And has a phone that emits a single ringing tone of 440 Hertz. Unfortunately, he drops it, so it falls off the edge of the 0.70 meters high top floor ledge. So we've got a measurement here of 0.700, 3 significant figures, meters. Sometime later, so this is dropping down here, and that's just that height that we're dealing with there. Sometime later, here's a reduced frequency of 416.2 Hertz. So let's just write these down. Our F is equal to 440 Hertz. We know we're going to deal with the Doppler effect formula. Our F dash, our F as it's heard, is 416.2 Hertz. The height of each floor is 3.10 meters. So every floor you've got we'll just call that H, which equals this. trying to cut down all the mathematical stuff where I can, but I'm helping to identify the parts of it. You may calculate the number of floors the phone must have fallen when it emits the wave that Ben hears as 416.2 Hz tone. State any assumptions made. Okay, I'm going to state the assumptions first because that determines how we calculate it. So one of the assumptions is going to be that G is constant and there's no air resistance, because if there was air resistance then the phone might reach terminal velocity. So we're assuming there's no terminal velocity reached, so it's constantly accelerating, and therefore it's accelerating from an initial velocity of 0 down to a velocity we don't know. We don't know the time or the distance, but we do know enough with gravity, force due to gravity, or acceleration due to gravity, that we could use a kinematic equation to find V, to find the final velocity at the point where here's the 416 Hz tone. Okay, once you have that final velocity, now you've got enough for the Doppler effect equation. So you can use f dash equals f naught, you have both of those numbers, times by the velocity of the wave, which is 340 meters per second, over the velocity of the wave. Let's see, it's a higher, no it's not, it's a lower tone, so that means we have to have the Doppler, the VW over VW plus or minus VS equaling greater than 1, so that means we are subtracting the velocity of the source. Is that right? No, it's lower, so we have to add it, so we have less than 1, because we're making f naught to go smaller. So so this portion VW over VW plus VS must be less than 1 to make that happen. Okay, I always go back to that because for some reason it never sticks with me. Okay, so we can use that then to find the velocity of the source, which is the velocity of the phone at that point, and then we can, I don't even know if we need to find, yeah we do. I think we have to do that one first actually. Once we've got the velocity of the source, we've got enough information to substitute it into a kinematic equation to find the distance, the total distance that it's fallen. Then we have to take off the 0.70 meters at the start, then we have to divide what's left by the number, the height of each floor. That'll tell us how many floors we get to. So I think that gives you enough information. If you didn't catch that, let's restate it really quickly. Okay, so use the information given to find, let's just go to a different color so I can circle things as we go. Use the information given and the Doppler effect formula to find the final velocity at the point where the phone is producing this tone that's heard, 416.2 Hz. Okay, then use that final velocity plus the other information known in a kinematic equation to find the distance that it's fallen through, this distance that it's fallen through. We take off the 0.700 meters at the start and then divide by the height of each floor to find how many floors it's gone. So remember, the whole thing was to calculate the number of floors. Oh, great one. Okay, moving on. D. Frankie is watching Ben from the top of an adjacent identical building. Okay, that's nice. So we've got our original situation here with his phone, and the phone drops off, and we've got Frankie. So this is Ben, and we've got, okay, I just paused by accident bumping my finger, hopefully I haven't lost anything, but on the left we've got Ben, on the right we've got Frankie, and Ben has dropped his phone. Frankie is observing. We're 40 meters away. In fact, 40.0 meters away. We're given to 3 significant figures, and what we have to find out is what would Frankie hear for the wave that Ben hears is 416.2 Hz tone. And this is actually not as difficult as it seems. We know the distance down here now. I think it was something like 20 meters or You'll have to check on your previous answer. I didn't do the calculation because we're interested more in the method. You need to know the angle here to be able to calculate the relative velocity, which will be the distance over the time of the fall. Is that instantaneous? No. You'd have to use the velocity, the final velocity at this point where the phone is here producing the 416.2 Hertz tone. So that velocity at that point, using the angle that you calculate from the geometric information of the spacing of the triangle, and that'll give you the relative velocity on the angle that Frankie hears. And then you just substitute it into your you're trying to find f dash here, you substitute it into your Doppler effect formula, because the velocity of the wave is still the same. Velocity of the wave, and again we just saw it was plus the velocity of the source. So this is your new velocity of the source that you plug in there, and then that'll tell you how what you end up with. There we go.